Okay, so let me try to explain how this Zoom webinar works. I think from the attendees perspective, you will just see Q&A and the chat. It's okay. I think if you have questions, you can raise hands, I guess. There's an option to raise hand and ask questions in the Q&A and chat. So please use that if you have any questions and anything. And if anyone knows the answer, it's good to have an interactive way. Let's say if anyone knows it before the speaker sees, please do answer and have discussions. And thanks for registering. I think it's going to be a wonderful school. So today we have our speaker, Shaikot Jahan Shuvo. He is a PhD student at CUNY, and he'll give a review session on special theory of relativity and something about group theory. Okay, so yeah, maybe you can start, Shuvo.
All right. So hi, I guess. Hi everyone, and I hope you guys are doing well. So, the agenda is pretty simple. We'll just briefly review some contents from relativity that's gonna be relevant for the upcoming lectures that you guys will have, and then we'll just take a very short tour of some groups, mostly Lie groups, and I'll try to show you like just a very little of what groups are and what you can do with them. And when you attend those lectures on gauge theory, or when you attend lectures on uh, Dirac fields and stuff, you're gonna see more of it. With that in mind, so let's start. So our agendas for today, or today's lecture. The first one, like I want to dedicate the first half since this is a 2-hour talk. So I'll try to dedicate 1 hour to special relativity and 1 hour for group theory. But then again, so it's 2 hours. Maybe we won't be discussing all the technical details. I'll have to hand wave a lot of things. So please excuse me for that. But we'll try to cover as much as possible. All right. So the first one is review of special relativity. And here we will introduce something called index notation. If you're already familiar with index notation, or Einstein summation notation, you already know what it is. But if you're not, don't worry, we'll go through it in detail. And then we'll just talk about some dynamics and kinematics. So this is the special relativity part, and the second one, the second agenda of the second half of this talk is group theory. This will consist of what groups are, so a little bit of introduction. We'll talk about how groups relate to symmetry. Then talk about some abelian, non-abelian groups. Non-abelian and abelian groups. And we'll mostly focus on the Lie groups. Because as far as I know, this is the most important thing in energy physics. So we'll talk about that. All right, so anyone has any questions so far? This is just our agenda for the talk. No? Okay, fine. So let's start with special relativity, or SR. So the first thing you can ask, okay, why do we need special relativity? Well, because Galilean transformations, I'm assuming everyone knows what a Galilean transformation is. Everyone is familiar with classical mechanics. So Galilean transformation always doesn't work. And what happens is that if you apply them to Maxwell equations, you will see that the speed of light is not constant for a specific medium. It depends on how fast you are moving relative to each other. However, historically that's wrong, because people found in experiments, the Michelson-Morley experiment and all that. So So in some sense, Galilean transformation always doesn't work, especially when you are going up closer to light speed and stuff like that. So Galilean transformation is just an approximation that works well within the classical limit. So that was one of the motivations, and what we do over here, well, we try to modify it. We try to modify it so that it fits with the experiment and all that. So the core idea is the laws of physics should be the same in all inertial frames. What does that mean? Well, by inertial, I mean frames that move, frames that have a constant relative velocity for now. That's what I mean. That means there is no acceleration in between the frames. That's what I mean by inertial. And what do I mean by the laws of physics should be the same? Well, this means, let's say, this is one frame given by x and y, and this is another frame which is moving, let's say, along the x-axis for simplicity with velocity v, and let's call this x prime, y prime. If some person over here decides to measure things from x and y, and there's another person, let's call this person A and call this person B. So person A measures everything from x and y, and person B measures everything from x prime and y prime. And let's say there is some sort of a object over here, somewhere over here, and this object is flying past them. So obviously there is some sort of a force working on it. So if person A writes the force law as F of A, some mass of the object, the Newton's law and stuff, A of A, acceleration measured in frame A, person B should also write something like this, A of B, where A and B will be related by a linear transformation. Or so to say, force of A will be related with force of B with a linear transformation. So the structure of the law or the mathematical form of the law should be the same. That's what I mean by the laws of physics should be the same in all inertial frames. Any questions, comments? I'm not sure if Rakin can. Sorry, Rakin, can you do one thing? Can you just type in chat? Just to I would just want to see whether I can, whether I'm receiving a notification, just in case someone is typing, because I don't see anything.
I don't think you get a notification, but it's
Okay, but do you,
okay. Maybe you can do an hour of talk or maybe 40, 50 minutes of talk, and then
okay, okay,
finish. You
we'll
can
do
see
that.
the questions,
Okay,
address them, and then go back.
okay, fine. Okay, so that works as well. So yeah, so these are the obviously there are more events to it. I mean, I just try to summarize everything, but yeah, obviously there are more reasons for special doing special theory of relativity. Um, but yeah, this is the prime motivation. Like you want your laws to be the same. You want your laws to transform either linearly or multilinearly. You don't want any nonlinear transformation in between the frame because that doesn't make any sense. And this one-to-one correspondence is important because your linear transformation, whenever you have a linear transformation, you get a one-to-one correspondence of events because the events are physical. So for example, if you see one apple drop, sorry, so one apple is dropping from the tree or something like this. If you are sitting right in front of the tree and your friend, someone who's traveling at a rocket ship, if you guys don't have a one-to-one correspondence of this event, the apple falling from the tree, You will say, oh, the apple fell on the ground. No, that's something physical. That should be invariant, no matter where from, no matter which corner of the universe you're seeing it from, it should be invariant. So that's why this linear transformation, or sometimes people say multilinear transformation, is important. If you have a nonlinear transformation, uh, the one-to-one correspondence of an event doesn't work anymore. So what we do to fix Galilean transformations, if you recall, like in Galilean transformations, the positions are given like this. R is some position coordinate, V is the relative velocity, T is time, and T prime is T. Again, R prime is some distance. Let's say there's another object over here. Let's call that object X. Let's say this is some R prime. This is some R, and oops, I should have used a different color. Let's do that one. And this is VT. So if you use that vector law of triangles, you know, triangle addition law. I think they call it triangle addition law. I forgot the name, but whatever. So if you do this, you get the Galilean transformations pretty easily. And since people thought time is absolute, T prime should be equals to T. But this is only a limiting case. And we get rid of that limit when we do special theory of relativity. So what we can do to generalize this into a broader framework is we assume there is a linear transformation like the following. Again, let's draw the frames. Let's say this is X and Y, and this is X prime, Y prime. And and obviously there's a relative velocity of V in between them. So what we assume is that the most general form of transformation will look something like this. X prime equals to AX plus BT, and T prime equals to CX plus DT. Now you can set up any sort of experiments. I think there are many ways you can derive the Lorentz transformation. This is the Lorentz transformation I'm now talking about. So what you do, you need to now solve for this A, B, C, and D. And immediately when you write this transformations, these linear transformations, if you notice that until your say is 0, your the time measured or time interval measured on both frames are not absolute. So that is something interesting, right? Like time is not absolute. So again, this is again something I'm not going to derive. I'm just going to show you guys the result because there are many derivations in many textbooks, and we also need to save some time to discuss some other stuff. So I'm skipping this. Once someone solves for A, B, C, and D, the transformations look something like this. And T prime equals to gamma T minus X C squared, where gamma equals to 1 upon square root over 1 minus V squared by C squared. So now I'll explain what this means. This is gamma. Gamma is given by this. V is the relative velocity between the two frames. And what is X prime again? Well, we have our object X over here. Okay, let's not call it object X. What should I call it? Object S, let's say. So again, this is some just along the X coordinate, the X coordinate of X, sorry, S in X prime. So this is your X prime. And now you also see that T is transformed in not in a way how Galileo described, like T prime equals to T. Rather, it has some non-zero factors, and it also depends on the value of X. That is the guy who's in the XY frame measuring the X coordinate of that object and stuff. So this is your Lorentz transformation. And oops, sorry, my bad. this is your Lorentz transformation that immediately tells you that space and time are not two separate entities, that rather they're mixed. So this is one point of Lorentz transformation, because when you see there's a change in x, there's also a change in t, not just x itself. Whenever there's a change in x prime, you have a change in t and change in x as well. Same goes for t prime as well. So space and time, they get mixed. So we say Lorentz transformation mixes up space and time. So from here, I think people started to call, whenever they work in relativistic region, they call this place as space-time. They're intertwined with each other. And again, if you write down the laws again, gamma and t prime equals to, you will see many interesting steps, especially the one that strikes people the most. I mean, it struck me the most when I first read it, was the breakdown of simultaneity. What this means, let's try to figure up set up a thought experiment, and let's see what happens. Again, we'll work with our two simple frames, x and y, x prime, y prime. Let's say there's an event. Oh, before I move on, sorry. What we did over here is figuring out x primes and t primes in terms of x and t. You can also do the inverse as well. If you do the inverse, instead of a minus sign, you will pick up a plus sign. And why that happens? Well, you can take this as an exercise where you try to write x prime and t prime as a column vector or a column matrix, and find out a transformation matrix that takes x and t to x prime and t prime, and then try to find the inverse of it. So I'll leave that as an exercise. I'm not going to do it here. So if you do the inverse, it will look something like this. This is the inverse. All right. So now let's say there is an event that's happening. So an event will consist of at least two coordinates, one in space, one coordinate in space. I mean, for simplicity, assume you're working in, um, just x and t, for example. That's the most simplest thing you can set up. So let's say an event that will take place in some coordinate x and some time coordinate t. So once you have an event in this primed frame, and then set up another event in that primed frame, and let's say they are simultaneous. I mean, let's say two firecrackers that popped off at the same time in the primed frame. If that happens, the question is, how is the observer in the non-prime frame seeing this? Is it simultaneous in the non-prime frame as well or not? If we just use the math over here, just let's say I'm not digging into any physical importance, or I'm not trying to think of the physics problem as a physics problem, rather I'm just doing some maths. What would happen is I can use this guy. Oh, sorry, this should be a prime. I can use this transformation to figure out the time difference as gamma del t prime plus v del x. And obviously these two events, these two firecrackers sliding up, they are, let's say 2 meters apart, 3 meters apart. So there's a space like separation in between them. And c squared. However, in the primed frame, they're simultaneous. They go off simultaneously. So del t prime will go to 0. So what you see from the math is this is giving you gamma v del x prime c squared. So what does this mean? There is a time delay from the point of view of the observer in the non-prime frame, and this is a breakdown of simultaneity. So now let's forget the math. Let's say, okay, how do you explain this physically? Now think of it like this: forget all the math, forget all the transformations and everything. The speed of light, I didn't tell you this, but whenever you read special relativity, they say it's based on two postulates. The one I mentioned, the laws of physics are the same, or they transform linearly from one inertial frame to another. And the second one, I mean, it's only my personal opinion. I don't think it should be called a postulate. Rather, it's a fact. The speed of light in a certain medium is the same. I mean, the speed of light is finite. So what happens over here when the firecrackers go out, they emit some light, right? And how do you measure an event? By detecting some sort of a signal. For example, your eyes, they are some sort of detectors. They can detect visible lights. So in this case, assuming the observer itself is a detector, the firecracker that is closest to this observer in the non-prime frame sends off a signal from itself, and he catches it, let's say, at 12 a.m. at night, for example, just a numerical figure. And then the second firecracker, it also sends the same signal. However, there is a spatial distance or a space-like distance in between them. I don't want to use the word space-like because that really means something else, but there's the physical distance, let's say 2 miles or something, 2 miles or whatever. So what happens over here? He gets the yellow signal first, and then he catches the red signal. So yeah, even though it was simultaneous, let's say, and you might ask, okay, how are these two simultaneous in this frame? Okay, imagine someone who was standing like this. There is this line in the middle in the same distance. This is the primed observer. I don't know, Optimus Prime or something. So for this guy, these two events were simultaneous. However, when you go to the non-primed frame, the person detects these two light waves, and there is a finite time delay. That's what the Lorentz transformation tells you in terms of the moving, like how fast is this frame is moving, what is the distance between these two crackers, and in terms of the speed of light. And what you can do from here is that you can also find other interesting stuffs. I think everyone already knows about this, but I think I should mention it. So, and I'll give this as an exercise. Is the first one is the length contraction phenomena. Let's say, again, you have two frames. One is moving, the other one is not. This is the moving frame, for example, going with velocity v. And there's a scale, some meter scale or something that this primed observer has. And he has a wooden plank or something. And he measures the length of this plank as L, or you can say L0, it's up to you. The question is how this length transfers to or translates into the observer in the non-prime frame. You'll see that if you work out the transformations correctly, you'll see the observer in the non-prime frame, he will perceive the length to be shorter. So this is the popular length contraction thing. And then there is time dilation, like clocks move slower in a moving frame. Same thing happens instead of, so this is something you can do for yourself. And the second thing is called time dilation. You can again set up, again, these are all thought experiments, but in real life experiments, they have also proved. I especially know about the time dilation thing. It happened in 1971. I think the US people did it with some atomic clocks, like cesium clocks, and took them really high up in the air, and they experimentally verified this thing. And nowadays, it's the this experimental evidences are very available due to some unstable particle lifetimes. I think what were those particles called? Neutron, not neutron, sorry. I don't know. I'm not a particle physicist, so I forgot the particles thing. But if you're interested in particle physics, you can figure that out as well. So all of this, everything has been tested again and again, and so far no one proved it wrong. All right, so as I was saying, the time dilation setup. So let's say again you have these two frames. One is, let's say, stationary with relative to the ground. The other one is moving at a velocity v. And instead of two firecrackers going at a, you know, going at a distance, like the thing we had initially, they had a separation. What you can say is there is a time delay because two events need to happen so that you can measure a time delay or delta t. So let's say there's the event A and there's the event B, and the time delay between A and B in the prime frame is some del t prime, and they happen at the same point. That means del x would be 0. If you plug this information into the Lorentz transformation, you will see that the time difference measured in the non-prime frame, it's slower. So as if there were a clock over here, the person standing in the non-prime frame or the frame that is stationary with relative to the ground, this person will see that this clock is turning slow. And this also gives rise to the twin paradox, but there is a little bit of twin paradox is a little bit complicated because in twin paradox, you can use the special theory of relativity to get the correct result. However, there's the subtlety, and those of you who don't know, the twin paradox is something like this. Let's say you are someone who's standing on Earth, and you have a twin brother or sister. Someday a rocket ship comes. Your sibling decides to jump in it. It almost moves closer to the speed of light. So he's now here. Then it goes really far away in deep space. And let's say 5 years later, by 5 years, I mean 5 Earth years later, it comes back. What you will see is that your sibling hasn't aged that much. However, you have grown quite old. I mean, people usually don't get quite old in 5 years. So, instead of 5, you can just also think 50 years or something. So maybe at this point, when you guys departed, you were 20. So now you're 70, but your sibling looks pretty much like 30 or something like that. And this thing really happens. However, even though you can get the correct result using the Lorentz transformations, the time dilation formula, as people say, but there is a thing. When you go like this, going at a uniform velocity, your biological clock or the clock you are measuring and the clock your sibling is measuring, uh, there will be there won't be any difference. I mean, by won't be any difference, I mean, you will see your siblings' clock is going slow and all that stuff. But at the very beginning, we said all the laws of physics should be the same in all inertial frames. So you might ask, okay, he's coming back, and since the laws of physics are the same, and since you guys are aging, and aging is something invariant, how can I get old and my sibling is pretty young? Well, there is a discrepancy that happens because throughout this round trip, it's not just a constant velocity motion. First of all, you have to take off. There is an acceleration. Then, I mean, the discrepancy starts to happen from here when you take off. And then when you change your direction, you have to accelerate, right? Without acceleration, you can't change your motion's direction and stuff like that. So this is another point. And then before you land, there is another deceleration. It's not that complicated, but it does require a little bit of time and discussion to understand the twin paradox completely. So if you want, you can look into Klepner and Kolenkov. It's a mechanics book, and I think they do a great job of explaining this pretty well. And there is also this paradox of the barn and the farmer. I mean, and you will also find tons of paradox type problems in David Moran's book. So if you're interested, you can look into those things as well. So yeah, I just wanted to give this idea, like because I also had this question back in the days when I was first learning relativity, because this thing, the twin paradox didn't make any sense to me. But then I read Clipper and I was like, oh, okay, this is the reason. You see the discrepancy in real time. All right, so let's see how many. Oh, we still have 15. Oh God, we have only 15 minutes left of 1 hour. Time flies fast, huh? All right. So yeah, this is it. The Lorentz, once you know the Lorentz transformation, you can do essentially everything by yourself. For example, you can try to find how the relative velocity law transforms in between two frames. So I'll just write them down without driving them too much. Let's call this u of x prime and del of x prime, del t prime. I want to write what del x, I can write it as what? Gamma x minus vt. So I shouldn't write del t, and t prime I can write gamma del t minus v del x c squared. If you do a little bit of algebra, simplify things out, for example, canceling the gammas, dividing by these, so that you have everything in terms of the velocities of the corresponding frames, you will have something like this. U of x minus v, 1 minus v u x by c squared. So what this means, well, again, draw the frames, x prime, y prime. There is a tennis ball moving at, let's say, oops. There's a tennis ball moving at some ux. By ux, I mean the guy in the non-prime frame is measuring it to be ux. What is the guy in the prime frame measuring? That is ux prime. And it will be something like this, where again, the relative velocity or the relative speed, if you're considering a one-dimensional motion, is v. Similarly, you can go for finding how the acceleration laws transform and how the forces transform. Then from there on, just like in classical mechanics, you can find out the kinetic energy, potential, and even potential energy if you are considering a moving object, for example, magnetic fields and all that stuff. So this is the very basics of the kinematics that you can see. And we will move into the dynamics part. We'll mostly present the dynamics part's results, and I'll try to set up the thing that I said before, like how special relativity mixes up space and time. And from there on, we'll see Lorentz transformation again, but from a new point of view. And I'll try to introduce the index notion. So before I move on, let's take 5 minutes and see if I have any questions. I understand I'm going really fast but it's been already, I guess, 38 minutes, and we also have group 3 as well. So if you have any questions or comments, please, in the next 5 minutes. Stuff. Okay, so this is okay. All right, so these were the very basics. Again, it's a really digressed or very compressed way of saying all this. We are not going into any details. We are just mostly hand waving steps, just giving out the important details and stuff like that. All right, so now that you have your Lorentz transformations like this, is t minus vx by c squared. If you write them in a matrix format, it looks something like this. If, I always struggle with these things. Instead of t, let's say ct. When you do quantum field theory, you're gonna take c equals to 1. That's just a way, that's just like natural way of writing things. So how do you write this? I have to read everything off because I forget them all the time. X prime is x negative. Can someone mention if I'm doing any mistake or something? This is gamma x, gamma ct. Okay, cool. And you have, should I write ct or should I just write t? I don't know. Okay, let's write t only. I'll do t only. This is gamma c. And then I have gamma, and what do I have over here? E gamma c square. Is this correct? I'll just check them out. Right. Gamma x minus gamma ct. Okay, this is correct. T prime is gamma v by c squared x minus gamma t. Oh, fine, good. I did a good job. All right, so when you write your transformations like this, you are familiar with the rotation matrices in 2 dimensions or 3 dimensions. So the question now I want to ask is, can we write something down that this transformation or the Lorentz transformation keeps invariant? Like under Lorentz transformation, that quantity will be invariant. To answer that, what you can do, you can again set up a thought experiment. You are measuring the length of a stick, let's say. Let's do it like this. And you are using some light pulses for that. And let's say the time it takes for the light pulse to start from point A to point B and come back to point A again, so that you have the measurements and stuff. It's delta t. Light speed is c. And this should be equal to the length of the rod or the stick. Let's call it L. L squared is something everyone knows. If you are working in XYZ coordinates, it looks something like this, where this is equals to what? C delta squared, right? So now what you can write is del x squared, del y squared, del z squared, minus c del t whole squared equals to 0. Now, this doesn't necessarily give you anything interesting at first sight. However, if you try to do something, because this guy is, let's say stationary relative to the ground, instead of x and t's, if you work with x prime and t primes, try to use the Lorentz transformation shown above, plug this into this equation, and see what the right hand side becomes. You will find out that this is also 0. So from there on, what we can say is the Lorentz transformation is something that keeps this quantity, this del x square minus c del t square, invariant. From there on, we can say this ds is something known as the invariant interval. Which is c del t squared, or I'll just write it as c dt squared, c squared dt squared, dx squared, oops, dy squared, dz squared. And later I'll call this a mostly plus convention. You can also write it like c dt squared minus dx squared, dy squared, dz squared. This is another convention. This is known as the mostly minus convention, and it'll be clear in a few seconds. Like, why is that? Mostly minus sign or mostly minus convention. And this is the mostly plus convention. Okay. So why is this thing nice, or why is this thing important? Well, if let's forget about the y's and z's, because y prime and z prime are the same. We are not boosting, like some people said, like Lorentz boost, those gammas and stuff. That's a boost. We'll come back to this section later on. Like, what's a boost? It's just, just pushing it forward, like getting a boost, like, rocket engines and stuff like that kind of boost. So let's just write it like this: ds squared minus c. You know what? Let's try to adopt QFT convention. Let's say c equals to 1. So d squared, dd squared, dx squared. This looks like a hyperbolic equation, right? And this thing is interesting because the Lorentz transformation, that is from one inertial frame to another, this interval is invariant. So like I said, if you try to compute this quantity over here, you plug in the Lorentz transformations, and you'll get the same thing back. So this is one of the invariants under the Lorentz transformation. From here on, you can define something called a proper time. People call it proper time. I think most of the time it refers to the moving frame, because if ds prime squared equals to ds squared, you can write dt squared plus dx prime squared equals to dt squared and dx squared, something like this. Again, you have your frames. Oh god, we only have 1 hour left. Okay. Then what you can do, you can take an event in the prime frame, like 2 events in the prime frame at the same space point, not in the time point. So dx squared will be 0, and you will have something like this. Again, I'm working in c equals to 1 convention. You can work with c not equals to 1 and get essentially the same result. So now once you have this invariant interval, you can just play around with it to find the relation of the time intervals or the space intervals measured in different events and from different frames and all that. And there's another way you can write this ds squared as the following. This is dt squared dx 1 squared. Instead of xyz, let's call them dx1, dx2, and dx3. Now this is something I'm writing down. I think everyone can verify it because you just need to matrix multiply the whole thing. Okay, sorry, dt dx1, dx2, dx3. Or I can skip an I guess. Yeah, I'll do that. This is an identity matrix. T x1, x2, x3. I can even write it like this. So this ds square or the invariant interval is a new measurement for the length, or it's a replacement of the notion of length when you are working with in the space-time. Like in 3 dimensions, you have the r square thing, x square, y square, z square. However, when you incorporate time, you pick up a negative sign. So that's why I want to write it like this. And just to give you an idea, because this thing really looks like the 3D thing when you have a x, y, z, 1, 1, 1, and x, y, z, right? This is some r squared thing. So when you work with space-time, you pick up a minus sign because time, behaves a little bit differently than space itself. And now this is a good time to introduce the thing called metric. So this matrix over here, we are calling it a metric. And in particularly in special theory of relativity, this is known as the Minkowski metric. The one that you usually see in 3 dimensions, that's called an Euclidean metric. So this is an identity matrix, just a bit different in the first index, where you have a -1. If you work in mostly minus conventions, you will have minuses in the other 3, in front of the other 3 ones that is over here. All right, so this is the Minkowski metric, and usually it is written as this. I'll come back to this notation in a few bits. This is an eta, and these are the stuffs we call index. So just before I go into that thing, I just want to give you guys just some like how the dynamics transform, because I don't have much time. I have to go to the group theory part as well. If you want to compute it by yourself or look into any book, you'll see that the momentum from one frame to another, I think someone mentioned it, like, the relativistic mass thing. I'm coming to that. So the momentum of a particle, let's say there's a particle moving with okay, the particle is moving with velocity v, I guess, with the frame attached, the frame that is the prime. I mean, the particle is stuck inside the prime frame, and you are standing over here looking at the particle. You are asking what the momentum is. The momentum is given by this gamma mv. Now, someone asked something about the relativistic mass. Well, from here on, if you want to write it like this, let's say I want to write gamma m as m prime and v. Now it looks pretty nice, right? Just like the Newtonian thing. However, if you do consider Newtonian stuff, the kinetic energy is given by, again, some mv squared, in the non-relativistic regime. What if I write m prime, let's say capital M prime v squared, where capital M prime is given by 1/2 of small m, right? So does that mean as soon as the particle starts moving, does the mass reduce to half of, like, by 1/2? No, absolutely not. It's just some numerical constant, right? You get from doing working from the definition of the kinetic energy, like force dx, and then you integrate over the x and stuff. Same happens in relativity. So while it's, I think some people say, like, if you try to solve mathematical problems, it does become a little bit easier to think of the relativistic mass as a real thing. but I personally do not believe this is a thing. When you are detecting something, or you are actually plotting momentums, you are not plotting the mass or something like that. So just like this case, you have a numerical factor, because gamma was what? Gamma is dimensionless, right? It's a numerical factor. It's v squared by c squared, and there is a square root. And if v is less than c, this is just 1, right? So yeah, you can't write m prime equals to gamma m. I mean, you can, but you can't call this m prime as the new mass or the relativistic mass or something like that. I mean, that's what I know, and I'll even show it to you. Like, you can use Lorentz transformation, and once you introduce the notion of 4 vectors and you carry out and you try to carry out an computation of the 4 momentums, you try to construct an invariant out of it. The only invariant that will come is the mass. I mean, not the mass is squared. And that will lead to the famous result of v squared equals to p squared plus m squared. The energy formula that is very famous and stuff like that. Right. So where was I? Yeah, the dynamics for the first thing is momentum looks like this. And the total energy, the thing that I was talking about, the total energy is the square root over p squared plus m squared. Again, I'm using c equals to 1. If you're not using c equals to 1, it will look something like this: p squared c squared m squared c over 4. And I'll show a very short derivation of this, because if I use the Lorentz transformation, it's going to take a lot of time. So I'll just show you guys a short derivation of this after I introduce the 4 vectors and stuff like that. All right, so yeah, these are all the informations, bunch of formulas, a lot of stuff. So what I'm gonna do now, I'm gonna first introduce the index notation. Those of you already know index notation. I think everyone have seen it from the matrices and stuff. Then I'll construct or introduce the 4 vectors, the notion of 4 vectors and stuff. And finally, we'll end the discussion with on relativity, with showing that there is a thing called, p mu nu is equals to negative m squared. Stuff like that. I'll explain this at the very end. So for now, let's introduce the index notation. Again, if you have seen matrix multiplication, you already know what this is. Just for a brief review, let's say you have a column vector like this. You have some matrix over here. You have something like this. In index notation, you write it like ai equals to sum over j, where this is some mjk. Oops, jk. The live index is s, which has to be I. mij, b of j. This is your index notation, your regular matrix multiplication and stuff, right? Now what we're going to do, we're going to upgrade ourselves a little bit. Since we are lazy, we don't want to write the summation notation. And what we do is we take the symbol or take the letter that is being summed over, and we move one of it, in upstairs or something like this. We can even keep it downstairs, that's fine. So this, modification is something people call the Einstein summation convention, like where the index that is repeated is assumed to be summed over. So repeated index is equivalent to sum over. That means there is a summation symbol. So this is the notation we're going to adopt from now on. And mostly I'll stick with the Greek indices because I'm used to it. You can also stick with Latin indices if you want to. Now let's try to write the invariant interval first. We had it like this: dt squared, dx squared, sorry, x1, x2, x3. And we can write it like this: dx1, 1 dx2 dx3. Okay, now let's call this as what? Some dx mu transpose, something like this for now. We will call this as eta mu nu. I think this is the convention, like mostly people use a eta to denote the Minkowski metric. You can even use G if you want to, it's up to you. And then you have some dx mu, like this. So we have pretty much everything we want. We have taken down this big expression into a smaller expression. People usually don't care about the transpose, so they write it like this. I mean, they don't care about the transpose. I mean, they don't write the transpose explicitly because this dx mu should be a column vector. However, you have a row vector here, so you put the transpose in. So this is your invariant interval. And there is another reason when people write them upstairs and downstairs. Obviously, you can bring all the pure math you want. This is covariant, this is contravariant, blah, blah, blah. But for now, I don't care about all of this because this is flat space and I simply don't care when we're doing things in flat space. So the only reason you can think of, for convenience, setting aside all the rigors, they cancel out. Repeated index summed over, they cancel out. And the quantity on the left-hand side, it doesn't have an index. So whenever you have this cancellation, by cancellation, I mean a summation over, not a single index is left, you get something invariant. And in physics, you obviously want to construct invariant objects, right? Invariant objects out of things. So, like when you construct invariant objects, you know which things are not changing from one frame to another. Those are the physical things. So for example, okay, let's try to construct something. And before I move on, sorry, I wanted to introduce the 4-vector thing. So 4-vector is what? It's just a vector that has 4 entries, or it's a 4-dimensional vector, so to say, because you're working in 3 space and 1 time dimension. So the column matrices that you see over here, dt, dx1, dx2, dx3 equals to, I don't know, let's call it some dp or something. I don't know what you're gonna call it. Some dx bar, something. So this is like a 4-vector. In other words, like if you are very serious about relativity, you will say, oh, a 4-vector is something that transforms linearly under Lorentz transformation. That's another way of saying it. But I'm not being very formal, so I'll just call it a 4-vector. Like if you're taking the rigorness of the 4-vector definition seriously, you'll say, oh, it has to transform like a vector under Lorentz transformation. So that's what a 4-vector is. So now what we can do? We wrote the invariant interval in the index notation or 4-vector notation, whatever. Let's try to see if we can write down the Lorentz transformation there. And then we'll try to focus on the invariant stuffs. Again, we're writing the Lorentz transformation, but this time from just using a different notation. So what does Lorentz transformation do? It takes you from prime to non-prime frame or non-prime to prime frame, right? So I'll just write them like this. Should I use the upstairs index? Yeah, I should use the upstairs thing. So let's call this x prime mu, lambda mu nu, x of mu. Again, there is a summation over the new index. So what does this mean? Something we wrote before. This looks something like this. Gamma, what was it? You see, I forget things. Even I don't remember what the transformation is. Worked it out a few seconds ago. Okay, I'll just work it out again. So yeah, I can't remember any of these things. So I think it was negative gamma c. And here you have xt And what do you have next? T prime x, so this will be negative b by c squared, and there's a gamma, and there should be another gamma, something like this. We are writing this thing with the help of the index notation or the tensor notation of the, I don't know, Einstein summation convention, whatever. So you can verify this if you want to. Like if you want, let's say mu corresponds to 0 and 1, where 0 corresponds to t and 1 corresponds to x, you can verify, you'll get the, you can verify from this guy that you'll get this transformations back, you know, the Lorentz transformations and stuff. So I'll let that as an exercise as well. All right, so since I said, okay, if you somehow manage to cancel, if you somehow can manage to cancel out all the indices, you can construct an invariant. Let's try to construct some invariants, yeah? The first thing is dx mu, dx mu. And why this is invariant, you might ask. Let me show you this. Let's say you have the prime frames as this, x mu mu, x prime mu, sorry, x prime mu, and this is x prime, let's say mu. There's a summation over this thing, right? But you can use the Lorentz transformations since these are 4 vectors. So instead of this guy, I will write this as, since this is upstairs, should I use the upstairs or the downstairs? Okay, let's use downstairs because I want to keep it up. Okay, you know what? Before I set this, I want to show you another thing. Because other than that, it won't make any sense if you're seeing it for the first time. So this is something, some sort of an appendix or something. I'm assuming everyone knows the matrix inverses and all that stuff. So this lambda mu nu, this is a Lorentz transformation matrix. Same goes for lambda upstairs mu, downstairs mu, and so on. This is also Lorentz transformation matrix. And you have this thing as well. This is an identity. If this is the lambda matrix or the Lorentz transformation matrix, this is the inverse of that. So you get a chronic delta or the identity matrix. These two, you can think of it like this, these two cancel each other out, and mu and rho gives you the delta mu rho, where delta mu rho is 0 if mu is not equals to rho. I mean, and if they are equal to each other, it's 1. So this is some sort of an appendix unit for the thing that I'm going to do right now. So let's try to figure out how does this thing look like. So I'll write it like this first, and then I'll have this as well. Again, we're working in components, like I call it the component notation as well. So you can move things around without worrying about whether 2 matrices are commuting or not. So instead of mu, let's call it a mu. And instead of this, oops, right. B, this B, and I have something like this. These B's cancel out and you get a mu. Yeah. So I'm writing the right hand side solely based on the Lorentz transformation. It's just a gymnastic with the index being upstairs and downstairs and stuff. All right. So now these are again components, matrix components or numbers, so you can flip them around. So this looks something like this. x of a, x of b. And using the identity that I showed over here, which really means lambda times lambda inverse 1 equals to the identity matrix, you can write a delta BA x of a, x of b, which really means this is just x of a and x of a. It doesn't matter, you can also keep b if you want to. So x prime of mu equals to x of a, x of b, sorry, x of a. So this is like an invariant. Like if this x is a 4 vector, you can take the dot product. This really means the dot product. Or if you want to be fancy, you can call it an inner product. And this produces an invariant quantity. For example, if you work with the dx, it will give you the invariant interval. If you work with the 4 velocities, you cannot, I don't think you can do it with the 4 velocities, but you can do it with the 4 momentums. And when you introduce 4 momentums, yeah, I think you can even do it with the velocity, and I think it should give you the speed of light. So try that one as well. So what you do, you can construct the 4 velocity vector. But to do that, you need the proper time thing. By proper time, I just want to say like proper time, you can think of it something like this. Let's say in the prime frame, you have something like d tau square, dx square, and ds square is, dt square plus, oops, sorry, it should be prime, and dx square. So proper time is, how do I say this? What's a good way of saying this? Is the time difference or the time interval, because whenever we are saying time, you cannot measure a single time, you can measure a time interval. So this proper time interval or proper time is something that you measure in the frame that is moving with respect to the ground. In that sense, if there is an event where there is no space interval, that means in the place, in the moving coordinates, let's say there is no space interval in between the events, you can take this to be 0, and then this d tau will be called proper time, even though till this era, I don't know what's so proper about it, but yeah, this will help you to construct a 4 velocity vector, which in turn will help you to construct the 4 momentum vector. And I'll just give you the answer for the 4 momentum vector, and it looks something like this. Let's call this P upstairs mu. And it will look something like this. If I'm not making a sign mistake, this is the energy. And then you have your, since we're working with, I mean, it's a choice, so it doesn't matter. I'll work with the negative and mostly positive part. This is Px, Py, Pz. So these are your usual momentums, the 3-dimensional momentums. And this is sometimes written as P0, the 0th component of the 4 vector of the 4 momentum, which is known as the energy. And then you can construct another invariant quantity, and this will give you negative m square, which will really mean p mu m square equals to 0. So this tells you another thing, that the mass, or what some people call the rest mass, is Lorentz invariant. Again, I'm already taking too much time for this, so I'm not showing enough this. So this is an exercise again. You can even find this in Taylor's classical mechanics. I think they prove it very nicely, like how this mass doesn't change under Lorentz transformation. Yeah, so there's a lot of stuff that we wanted to talk about, and I'm not sure if I have, because I don't have much time. We talked a lot, and yet we talked about nothing because there's a lot of stuff to be covered. So yeah, you can construct this invariant quantities. This is the index notation. You're gonna need it when you do QFT. And there is one last thing that you should know is if I write this upstairs mu, if someone brings in the covariant and the contravariant and the metric, okay, metric is something, some sort of a transform that takes you from the co to contra, the covariant to contravariant or contravariant to covariant and stuff like that. So I'm not saying all of that. I'm just saying take like if you know this, good. If you're someone who has never seen it before, for now, for the next few weeks, just believe in the stuff that I'm writing right now. You can write it like this. Oops, I made a mistake. So metric is something that you use to move the indices up and down, because when you do a QFT, there's going to be a lot of algebra. That's gonna come in terms of the metric and stuff. So you think of it like this, cancel the v's, or mu is left, so mu goes over here. Again, a very, very wrong way of doing all of this, but we are short on time, so I guess this will have to do. But then again, if you are deeply interested in this, read any book on tensor analysis or general theory of relativity. I think all of them give a fair treatment to this index gymnastics, or even the QFT books like the Peskin. Peskin is a pretty nice book, I guess. So this is one way of doing this. And what you should do, you should try, let's say I have a set of coordinates, or a vector like this, let's say x0, negative x1, negative x2, negative x3. And I'm calling this the upstairs x mu. Find what is downstairs x mu. And again, remember this eta mu nu is 1, 1, 1, 1. It's a 4x4 matrix that has all the elements as 0, just ones in the diagonal, but for the downstairs indices, there's the -1 sign. In fact, if you want to do another exercise, try to figure out the inverse of this. I mean, this is not people will say, oh, this is not a proper way to write a matrix. You should write just eta. But, I'm just accustomed to this sort of notation, because when you write indices, you're essentially referring to components. But whatever, we're doing physics, we don't care. So try to figure out the inverse matrix of this. From there on, you can go and try going from this upstairs to downstairs. I think that will help. And the last thing that I wanted to show but couldn't is, let's say, I want you guys to prove this transformation law. I mean, we are doing Lorentz transformations, right? We already said how the coordinates transform under Lorentz transformations. So my next question is, how does the metric, the eta, this is a matrix notation, by the way, in case you get confused, like these are matrices. So, and if you want to write it in terms of the index notation, you can do it like this, I guess. Oops, alpha mu, alpha beta. I guess this should be beta, something like this. See if you can prove this, like the transformed metric, like the transform Minkowski metric looks like this. This is how the metric transforms under Lorentz transformation. And a very good starting point is to just say this is an invariant thing, and then write ds squared as eta mu nu dx mu, and you do the similar thing for ds prime squared, and then you use the Lorentz transformations, and you should be able to arrive at this conclusion. In fact, this is the very thing that defines the Lorentz group. Like, not as hardcore as Peskin, go for Shonkor's quantum mechanics. All right, so we don't have much time. Officially, we have 19 minutes, but obviously it's gonna take more than half an hour. So seatbelts up, everyone. So now we are done butchering relativity. I think I butchered it. Yeah. So, oh yeah. And yeah, so we'll take a very short tour, like a 30-minute crash course on group theory. And you guys are gonna be experts, after 30 minutes. Like you can go and, I don't tell people like, hey, I learned groups in 30 minutes. So, okay, so what is a group? Before I answer that, why do we need groups? Well, groups help us to study symmetries. Why do you need symmetries? We love symmetries. Symmetries makes our lives easier, reduces the degree of, uh, the degree of freedoms and stuff. Once you know something is constant, something is conserved, something has a symmetry, you can just throw that thing out. And at the same time, it gives you some really important information like what are the conserved charges and stuff. So that's the motivation of group theory, in short. So motivation, we love symmetries. Symmetries and groups help us to identify those symmetries. Symmetries, sorry, my handwriting is pretty bad. How? Well, a very short example is you can take a triangle. No, it doesn't autocorrect. Okay. So let's say this is a triangle, and not just any triangle, it's a equilateral triangle. And let's say there is a, oops. I'm so bad with using this application like that. So let's say there's a line going through, it's a perpendicular bisector. This is an equilateral triangle. What you can do, you can flip this triangle around these axes. You can rotate this triangle, like, take this point, rotate it up to there. You can flip it, like this. You can flip it over to this, along this edge, all these edges. Whatever you do, this triangle remains the same. So that's pretty nice. It's a symmetry. So what can we consider something as conserved? Well, the structure of the triangle, the area of the triangle, the perimeter, and all those stuffs, So this is what groups tell you. Like it gives you the ideas of the symmetry, and you will realize this more when you are doing the quantum field theory, and you'll see there are structures that emerge that tells you about the symmetry of the theory. Because I think you have already seen people talking about we have this symmetry, that symmetry in the theories and stuff like that. So this is one example. Another very familiar example is, I'm not sure if I should give this example right now, but okay, whatever. I'm gonna give it anyways. People call it the U1 symmetry, unitary symmetry. If you're already familiar with quantum mechanics, you know what it is. If you're not familiar with quantum mechanics, don't worry. This just really means you have something like this, you have a variety or something like that. Obviously, there's a Hamiltonian, but I don't care about the dimensions right now. So let's say you talk about some z bar, some complex number, z belongs to the complex plane of something like that. And if you take the mod z square, which really means z bar, you already know this is something invariant under this sort of transformations. So this is another example of symmetries and stuff. And obviously, if you are, again, if you know the Lagrangian formulation, you heard about Noether's theorem. Noether's theorem gives you what? Noether's theorem gives you the charges from those symmetries. You have some charges, those are your conserved quantities like momentum, By charge, I don't mean the electrical charge. It's just a way of saying the quantity. You know. So this is the motivation for starting the groups. That's it. Yeah. And you will find more motivation as you go along with the, the main lectures of the school. So I'll just introduce the definition of a group. Definition of a group. It generally satisfies four axioms. I think mathematicians call them axioms. So what is a group? It's a, I mean, should I say set? Yeah, I think so. I mean, again, forgive me. I'm not a mathematician. I don't know all the formal languages and stuff. And so with that in mind, I'll define the group in the following way. Let's say I have a set of items. A group is a set. It's a set with elements. Let's say I'm calling them small gi. This is an index just to identify different objects from the set capital G with a binary operation. If you ask what a binary operation is, it just takes like two things and then do something to it. Yeah, that's a binary operation. With a binary operation, how should I represent the binary operation? With a circle, let's say, so that the following axioms are satisfied. Number one, for all gi belongs to G, for all gj belongs to G, if I do gi with gj, it should give me some gk, which also belongs to G. And at this point, when I'm talking about the definition, these things don't have any representation at all. These are not numbers, these are not matrices, these are not anything. They are abstract, absolutely abstract, and there is no representation for it. So for now, bear with me. We'll go into representation very soon. I'm just, maintaining the formality of giving you guys the definition. So this is one of the first axiom. Like if gi belongs to the set, gj belongs to set, then gi with gj, it should give you some gk that will also belong to the set itself. I think they call it the closure property or something like that, but that doesn't really matter. But I think they call it closure. I mean, if I recall correctly, obviously. I read these things a few years ago, so I don't remember any of this. So the next thing is associativity, I think. This seems very natural. Gi, gj, and then let's say you have, since this is a binary operation, you do gi with gj first, then you have gk, and this is equals to gi, gj, gk. So what this essentially means that order of multiplication. Sometimes this binary operation is also called a group multiplication, so that's another word to keep in mind. It depends on the author, how they're writing the whole thing. So you can say the order of operations or the order of multiplication doesn't matter. So since I called it a binary operator, so I'll just call it order of operation. Doesn't matter. Then the third thing is existence of identity. So there should be existence of identity. How do I write this on? We should have, there should be some g of e belongs to capital G, such that g of e, binary operation with g of I equals to g of I, binary operation with g of e equals to g of I. In that case, this g of e is known as the identity operation. Sometimes people call it the do nothing operation. And the reason people write it like this, you might think, okay, g of I times g of e or g of e times g of I, they're the same thing, but not necessarily, and we'll see that in a few moments. So if that happens, people call it the abelian group. If it doesn't happen, it's the non-abelian groups, where things commute and don't commute and stuff like that. So we'll catch this very soon. So this is the existence of identity. And finally, the last one, the existence of inverse. So there should be some gi belongs to capital G such that gi, sorry, you know what, let's write it like this, gi of, I'm using really bad notation over here, maybe I could simplify it, but I don't know. This is some element, g small I of capital I, and if it acts with gi, this will give you g of e back. This is true as well. If you find any set and if you find any set and find a binary operation for them that satisfies all of these axioms, they can be called a group. So now let's see a few examples, and this example will also serve as a representation of the group. Since these were all abstract objects, let's consider the set of all real numbers. That means I don't know, all the negative numbers, -5, -4, 3, 2, 1, 0, +1, +2, and stuff. You can show that this forms a group under the binary operation plus or minus, if I'm not wrong. Yeah, plus and minus. Yep, this will form a group. 0 will act as the identity because 0 plus something is that thing, like 5 plus 0 is 0. So this will form a group under this operation and this operation. You can check it for yourself, like all these axioms, they get satisfied. However, if you take the set of real numbers and try to introduce multiplication as a binary operation, you will see that that simply won't work because there is no inverse of 0. I don't know if that makes sense. You can find an identity because in multiplication, identity will be 1. However, if you have 0, again, identity is 1, but what's the inverse of 0? What is the number that you multiply with 0 and gives you 1? There's no number such as that, So if you want to form a group within multiplication, you can consider a set R, R plus, I think that's how they write it, 1, yeah, I think if I'm not wrong, this will form a group under multiplication as well. So these are stuffs from numbers and stuff, and they're fairly easy to see. And also what you see, like if you have a group within the plus or minus or multiplication, those group operations, they commute because 2 times, let's say if you consider multiplication, 2 times 5 times 3, it really doesn't matter how you multiply and all that stuff, right? Right, it's gonna be the same thing as 2, 5, 3, or like this is associativity, but then you can do 2, 3, 5. I mean, this is pretty ordinary. You can they commute, all these numbers commute and stuff, but things do get a bit weird when you're not working with numbers. And whenever you have this commutation stuff, let's say 2 plus 3 plus 5, you can also write it as 2 plus 5 plus 3, or just like this guy. Since these elements, in terms of the operation that you're doing, they can commute and they still give the same result, we usually call it the abelian group. I think they call it abelian, not abelian, or abel, I don't know. Abelian group. By Henry Cables or something. I don't remember his full name as well. So this is the abelian group. So abelian groups are groups where the group elements commute when you are doing the binary operation. And then you will have non-abelian groups where the group multiplication is non-commutative or the group operation is non-commutative. Okay, so abelian group refers to commutative. Just in case anyone doesn't know what do I mean by commutation or commutative, it's like saying AB equals to BA. This is commutative. And now instead of numbers, I'll show you one in the other example, and this will consist of the non-abelian groups. Think of matrices. Okay, let's say 2 by 2 matrices for now. We are not considering the general stuff. So let's say I have a set full of those 2 by 2 matrices where the elements are real numbers. So let's say I call this set some M2. So the elements are matrices again. These are 2 by 2 matrices. I'm indexing them with I, and such that MAB or M mu nu, so matrix elements belongs to the real numbers. And these are again 2 by 2 matrices. Then what you can do is you can show that these matrices under matrix addition, again, the binary operation is not just plus, it's matrix addition. Under matrix addition, they will form a group. Again, this will be an additive group too, because if you have two matrices A and B, let's say they belong to M2, A plus B equals to B plus A. You can show that for any general n by n matrices under standard matrix addition. So this is again an abelian group. However, if you consider matrix multiplication, the commutation property or the commutative property is not there anymore. Like if you have n by n matrices, let's say, let's do the most general thing. We're done with the special things. Let's do the n by n thing. So you have a set of n by n matrices filled up with real numbers, and you want to see whether you can find a group within this matrices by using matrix multiplication as a binary operation or group multiplication operator. The answer is no. Why? Because you will have a 0 by 0 matrix, all the elements are 0. How are you going to invert it? You can even find other matrices that doesn't have an inverse, because to be a group, you need to have some sort of an inverse, right? So to have an inverse, let's just put an extra constraint of having the non-zero determinant. Let's say I have some element of this set, which I call A or AI, whatever. The determinant should be non-zero so that it's invertible. And then you can show that this matrix, this set of matrix, that means the n by n matrices with all real entries who are invertible, that means non-zero determinant, will form a group under standard matrix multiplication. I think you guys should take this and exercises. Like if you have already done it in your life, you don't need to do it again. But if you're someone new who haven't seen it, just give it a try. So once you establish the fact that matrix multiplication does form a group, for this case that we're talking about right now, you already know something very basic from high school. Like if these are two matrices, this is not always true. Like AB is equals to B. It might happen, but it might not happen as well. And in general, it doesn't happen. When it doesn't happen, we call them non-abelian groups. So if this A and B are group elements, these group elements do not commute with each other. Do not commute with each other. And there is an official way of writing down the non-commutativity. This is something we'll see tomorrow. This is a commutator, which is A and B. AB minus BA. If this thing is 0, they commute. If this thing is non-zero, they don't commute. All right. So these are some basic definitions and stuff. You know, what are groups, and there's a lot of discussion about what are there's subgroups, there are normal groups, normal subgroups, there is Lagrange's theorem, left coset, right coset, blah blah blah, tons of formal stuff. Not going through any of it, because yeah, I don't think you're gonna need it anyways. At the same time, we don't have time. So, and this is not a group theory course, it's just a crash course. So I have my excuses, you know. So yeah, so this is the very definition of a group, and they help you to identify symmetries. Again, you're gonna see it pretty soon, hopefully in the main school lectures. My job is to just give you some little bit of technical ideas about this stuff. So now, what do I want to talk about? Let's give you the definition of discrete and continuous groups as well. I'll give you the definition of a discrete and continuous groups, and then we'll move on to the Lie groups and stuff. So discrete group means the elements are discrete, finite, and stuff. And when you have a continuous group, that means um, you have a continuous numbers of. Again, I'm saying this very informally. If you're a mathematician, you're gonna get triggered by it. So yeah, continuous means it's just continuous. That's it. Tons of elements. Like now, don't ask me if this is finitely like is it what do you guys call it, like a finite, infinitely countable or finite countable? They have all sorts of technical terms. So discrete means you think of it like this: you have a finite number of elements that you can count, and continuous is like you can't count. And okay, what's next? Discrete group, continuous groups, and then we move on to Lie groups, right? Yep. So before I move on, so far I just only talked about definitions. Do you have any questions? Like if you have, let's take 5 minutes and listen to the questions and discuss among ourselves. I'll open up the chat. We have 8 more new. Okay, is there any good price metrics? Okay, this is something. It is indeed closure. Yeah, I'm just really horrible with all these formal names like closures and yeah, I forget them. So I always say, oh, this is what I think, because you know, I might be wrong. Shouldn't it be the case for abelian groups only? What are the order of operations? Oh, no. When you do the second point, associativity, you see there is Ji, G of I, G of J, and G of K, right? Let me just go back. I think I'm trying to show on the wrong one. Oops, sorry. Where are the axioms? Ah, there you see. You see, the order of multiplication, or you know, the like you do Gi and G of J first, right? And then you have here you have G of J and G of K. So it does not mean like you can exchange these two. Like you cannot exchange Gi and G of J. You cannot move them from their own places, you know. It's think of it, okay, forget about the abstract stuff. Just think of it as matrix multiplication. If you have matrix multiplication, you can do A, B, C with, let's say you are multiplying A and B first, then you are multiplying the result with C, right? This is the same as A with B and C. it has nothing to do with commutativity or non-commutativity, right? Now, if you want to do it like this, let's say instead of AB, you want to write BA. Is that valid? No, that's not, because you don't know whether A and B commute or not. So this associativity really means the brackets don't matter. That means it doesn't matter which result you bring in first, it's gonna be the same thing always. It's just like matrix, how matrix multiplication is associative. Does it make any sense? I think it should. Like, yeah. Yeah. So then, oh, someone also answered it. The order of elements being operated, which is not described. Which is okay. Are these preschools of sessions of student all also be uploaded in YouTube? Yes, as far as I know. Are the continuous group and league groups the same thing? Nian, I don't exactly remember this answer right now because it's been a while. But I don't want, because I don't want to comment on this right now because I might be wrong. If I comment on this thing, I might be wrong. But for Lie groups, you do have a parameter. Lie groups are characterized by parameters. Finite groups are not. Finite groups are Lie groups. What? As I was saying, sorry, I got distracted by seeing another comment. Lie groups are described by a continuous parameter. Now, if you have a continuous parameter, what do you do then? Do you get infinite amount of elements? I don't think that's the case, right? Because if you take a continuous parameter, you also need a generator to generate a group element. But then again, your parameter is continuous, so if you continuously vary the parameter, the group elements vary too, you know. So, but I don't want to comment on it right now. I'll need to see it. I need to see the details and then I can comment on it. Okay, so finite groups or Lie groups implies that there are some Lie groups which are not continuous. Why should Lie groups be not continuous? Finite groups can be seen as a zero-dimensional. Again, I don't know about these manifolds things that you guys are talking about. I'm not familiar with those. The only Lie group stuffs I know, again, I think Nian is talking from a very mathematical point of view. I'm not talking from a very mathematical point of view. I'm talking from more like a high energy physics point of view. So I don't know about this. Yeah, Lie groups are manifolds. That's what something I read years back, but I never really cared that much. So yeah, I cannot comment of any of the thing Nian said. This is more mathematically rigorous questions. I don't want to comment about those things because if I do it, there's a chance I'm gonna be wrong because I haven't studied those parts yet mathematically. Any more questions? Anyone? Question, comments, or concerns? If you are someone who have never studied group theory, and if you're someone who's okay, so it totally depends, all right? So if you are someone who wants to do rigorous math, I'm not the guy to suggest you anything. I've never done any rigorous math. I only care about it because of the physics. Um, if you're more mathematically inclined, I guess talk to a mathematician. If you're talking with me, and you are a beginner, you have never seen group theory, go for I don't remember the right answer anyway. I think it's called Symmetries and Particle Physics by Robinson. Coming from engineering background, haven't seen. Okay, go for Robinson's book. Oh, tomorrow's agenda, it's quantum mechanics. Mostly the harmonic oscillator. And if I get time, then we're gonna do Dirac, some preliminary Dirac equation. That's it. Yeah, so go for Robinson's book. I guess that's pretty lightweight. And yeah, and there are tons of group theory books. There are appendix of Peskin's book as well. And there is a book by Lee Group. Oh my god, I don't remember any of the writer's name right now. But I do remember the title. It's called Lie Groups and Lie Algebra for Particle Physicists. Then there's another book by Georgi, but I haven't read it yet. Uh, it's called Lie Algebra for Particle Physics. But he mostly does representation theories in there. So it totally depends, like what sort of group theory you wanna do, Dave. Anything to refer anything to refer before tomorrow's session? I don't think you will need anything because for tomorrow's thing, that's the most important thing. We're gonna take some time, and if you want, you can read Griffiths, you can read Shankar, you can read Sakurai, anything on quantum mechanics. Okay. Someone also suggested Group Theory in Physics by Z. Yes, these books are pretty nice, I guess. Again, I haven't read any of the Z's book as well. So yeah, there are tons of stuffs out there. It depends on what you wanna do. Do you wanna do hardcore pure math? Do you wanna do some representation theory? Do you wanna do particle physics only? It depends. All right, so I think there's a discussion going on. There's another suggestion and introduction to theory of groups by Rotman. Again, these are very good suggestions coming from everyone, so that's good. Even I don't know this much resources. All right, so I think I should move on. Nian, are you talking to me like can zero-dimensional point like manifolds be seen as continuous as well? The continuous function just being constant? No idea. I don't know. Sorry, not an expert on manifolds. Mm, okay, so I think we can move on and we can jump into Lie groups because that's the main thing we're gonna need for this school, I guess. Lie groups. For us, who doesn't do I like very informally, who does informal stuff and says informal stuffs all the time. These are groups characterized by a continuous parameter. Uh, a very simple example is the circle itself. You have a circle. Oops. Then you can think of these rotations as symmetric transformations, like rotations from one point to other. I should have used a different color. So this angle theta, the rotation angle, it's a continuous parameter. I think everyone will agree with this. And this rotations, again, if you write a rotation matrix, something that comes from conserving this two-dimensional length or something. Yeah, whatever you want to call it. This R transpose, the inner product, dot product, whatever. The quantity or the transformation matrix, I think it comes as a cosine theta, sine theta. I might be wrong with the minus signs, I guess, depending on clockwise or counterclockwise. But I think, yeah, this is the correct one. Cos theta, sine theta, your determinant is 1. Okay, so this is correct. So this is the transformation. And this transformation keeps the circle invariant. So this is an example of a Lie group. And what you can do is you can actually show this two-dimensional transformations form a group. So I guess you can try to show that like a set with elements like this, they do form a group. So you can try to show that as well. It's a rotation group in 2D. And what's the conserved quantity? Well, if you know some classical mechanism, it's the angular momentum and stuff like that. So this is a very short example of how Lie groups should look like. And since it's design, sorry, and since it contains a parameter like continuous parameter, There is a way of building up Lie group elements, and that is through the generators. And we'll just show you like what these generators really are. So think of it like this. The groups we talked about so far, when I talked about the group definition, I said, okay, these are all abstract objects. So now what I want to do, I want to give them a representation. I don't want to deal with abstract objects. Just like we said, okay, think of numbers, think of matrices. So those are representations. So what I do, I give the groups a matrix representation, let's say. And from those representations, we'll try to figure out the generators, and then I'll give you guys some exercise, and then we'll be done with it. And you'll see later on how you can use these group generators to generate any sort of angular momentum algebra you want. Same goes for Lorentz group. Um, that will be very similar to the SU2 algebra. In fact, it will be a double cover of the SU2 Lie algebra and stuff like that. So yeah, I'm trying to really adjust a lot of information within a very short amount of time. So that's why it's very messed up. So we want to figure out the generators, but before that, we'll just give the group elements a representation. I'll call it rep. So let's say we have a group. Sometimes people write it like this, the set with the binary operation with our elements G1, G2, da 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 da. Then this D of Gi will be a representation for the group element Gi. And this representation will have to satisfy some constraint, and that will be given by D of Gi, some star. I'll explain what the star is. D of G equals to D of Gi, Gi. This is the group binary operation. So this is the group operation. I called it GO. And this is the operation on the representations. For example, if you want to give it a matrix representation, this operation might be matrix addition, matrix multiplication, and so on. So this is the representation operation. I'll call it rep op in short. And to find a way, to give this element some physical representation in terms of the familiar objects, we're going to use some linear algebra. And we'll use the bracket notation. Okay, let's just take a detour, just in case you don't know bracket notation. Yeah, so we'll say something like this. This is a cat. This is something we call a bra. And this cat will really mean a column vector. Again, I'm saying this informally, not being a mathematician, because for them it's a abstract vector. Yeah. Even physicists use them as an abstract vector, and then they use representation, but at some point people just don't care. It is just a vector, that's it. And this is a row vector. And this is like, if you already know about this, great. If you don't know, for now, you can think of it like this. As you do more reading, you're gonna get familiar with all the abstract stuff, and you're gonna get comfortable with it. So this is the bracket notation. So the representation will satisfy this constraint. Sorry, I already wrote that. And we will assign the group elements to this abstract vector where we have this orthogonality condition. Oops, did I write not equal? It should be equal. Like if they're the same, they're orthogonal. Some people even call it normalized and stuff. And if they are not, then this is 0. Like if they're not the same, this is 0. Okay. So this will enable us to find derive a scheme to find the representations of the groups. And with the help of this, like this is a vector, and since we want to give it a matrix representation, this will be a matrix, and it will act on this abstract ket, or the ket vector, or the column vector, whatever you want to call it, and it will take it to, oops, sorry, something like this. Like this is, for now, this is, take this as the definition of the how the representation transforms among themselves. So what this really means is that you take a group element, represent it with a vector. You take a group element, and this transformations, it's a linear transformation, since we're doing a matrix transformation. I mean, sorry, matrix representation. Whatever happens in the abstract space gets magnified within the matrix space, like where you're seeing things with matrix and column vectors. So within that point of view, it's equivalent to say, oh, I'm doing GI with GJ, and this is giving me some element of the group itself. And the equivalent of that when you are talking in terms of matrix is you have a matrix, you have a column vector, and this will give you some other column vector that doesn't leave the vector space. So, I mean, this is how you can think of it for now. And if you accept this, then you have a way of finding out what this d of gi is. You can just multiply this with, let's say gk, d of gi, g of j, g of k, g of I, g of j. Sorry, it should be k. Right, and this is the this will be called the element of this matrix. Let's say kj element, and this is some gk, gri, gj. So this will help us to build the representations of different groups. If you want, I think you went, okay, let's not, okay, you're not gonna need it later, so maybe I'll just type in a few exercises, give you guys some hint, and we'll send this to Rakin, and you're gonna use this to represent different sort of groups, like the cyclic groups, yeah, cyclic groups, rotation groups, and all that. I think instead of discussing it here and discussing the solution here, I should just type a guided exercise and send it out later. Yeah, because we're already over our due time. Yeah, we're already 24 minutes over. So the last thing that you need to know a little bit about is after you do the representations, you need to know the generators. So you know what? I'm just gonna state the result, and I'm gonna give the statement how you can derive this statement as an exercise. Yeah, I think that should save you guys some time too, because you're already late. The generator. So Lie groups are Lie groups are parameterized by some continuous parameters, and there are things called generators. That generator, along with the parameter, generates the Lie group. So let's say there's a Lie group element x of I. This is the group element. It can be a matrix, for example. And what happens is you can write this x of I with some e to the power I, let's say some p of I and some k of I. This p of I is a number type of thing, a parameter. And this k of I, for the convenience of our discussion, can be thought of as a matrix, which is also called a generator. So if you exponentiate this quantity, you'll get some x of I. This is the result. This is a big result. You can actually derive it. And some people were talking about Lie groups being manifolds. That's where the things come from as well. In fact, these generators, they live on the tangent space of the manifold because the generators are given by negative I dxi dpi, yeah, with p pi epsilon. So these are the statements, and we are already over our time. So um, I will make an exercise that will guide you through all of this, like the things about the generator. And the very last thing me and Rakin discussed before, like we wanted to cover Lorentz group, but now I realized it's not enough. Like we don't have enough time. So before I finish off, I'll just say, this thing I talked about when I was talking about relativity, this lambda transpose eta lambda, where it is a matrix, you can show that this sort of transformation forms a group, and that group is called the Lorentz group. And they will, so Lorentz group. Maybe I should give an exercise on Lorentz group as well, like if you guys want. And yeah, you can even find the representations for Lorentz transformations. I mean, the Lorentz group elements. You see the boost generators, the rotation generators. The boost generators are when you have a mixing of time and space. The rotations are just your ordinary rotations, like rotation in space. And from there on, you can figure out the rest of the thing. And you can even do it for arbitrary dimensions, and you will have this angular momentum operator. So JME knew this satisfies some algebras as well. And it's gonna be pretty interesting when you do the algebras and figure out what these results are. You can get spin half representations, left-handed spinners, right-handed spinners, spin zero representations, arbitrary spin representations, all sorts of stuff. Yep. Yeah, that's pretty much it. All of this comes from the Lorentz group, like the representations, different representations. If I recall correctly, okay, I shouldn't write it because I'm not sure about it right now. I think the representation set arbitrary dimension is something like this. Like if you represent them with matrices, that's what people do most of the time. It will be something like this. So it can be halves, like you can have a 0, 0 representation, 0, half, 0, half, half, so on. You can go up to the ladder. So it's a huge, like, again, special relativity, then group theory. Like what we did most of the, apart from the definition, we didn't do any group theory. That's a fact. All we did was doing the representations of groups. And these are huge topics. There are plenty of books on it. Depends on how much deep you want to dive in. My plan was to do a lot more, like show you guys the structure constant, Lie algebras and all that. But yeah, I don't think that time, we have already half past our allocated time. So yeah, unfortunately, I'll just stop here. So if you have any questions, I guess we can still have 5 or 10 minutes for the questions.